Hi, my name is Dennis. Welcome to Foundations Linux. Let's get started on our intro to Linux and systems architecture. So our learning objectives include to understand the components of the Linux OS, also known as the operating system. We want to be able to understand hardware requirements and how it works with the OS, and then finally translate business requirements to high-level system designs. First and foremost, operating system components include a variety of different items software, drivers, hardware, all working in unison to create the experience that you need to create that platform ultimately to what you'll build on a solution and ultimately your applications that run on this OS. OSs include Windows 10, iPhone iOS, Mac OS X, Ubuntu, Debian, and CentOS flavors of Linux, and many, many others. Among the high level components of an operating system, we have applications which really start off in the top stack of your use case experience. Applications are really programs, processes, or anything else that runs in a user land space. So the notion here is the user land. And then anything below that is where your operating system has the deeper security root controls. The kernel is a very specialized gatekeeper that takes input and output from your applications, interacts with the rest of your operating system components, and ultimately uses special software drivers to interact with your other input and output devices, which include CPU, which is central processor unit, memory, and other devices that are hardware based. Now, these are just some of the items and operating systems take a long time to create in a full method for end users to use, such as you and me. And the kernel is a large portion of it, and our applications are also a large portion of this. We'll see further on. Some of your applications include Microsoft Word, Chrome, any kind of mobile app, including Shazam. And really, they're all just code that runs over your operating system on top of it. They're usually compiled, which is different languages that need to be specially crafted to create binary machine learning, um, binary machine language that is, compiled specifically for an architecture. So your architecture of your operating system might run on Intel x86 64-bit, or it can run on an ARM processor such as your phone. That could be 32-bit or 64-bit. Other types of code include portable interpreted code. So other languages such as Ruby and Python and all these other scripting type languages utilizes an interpretative engine accordingly. That interpretative engine is installed on your operating system and allows you to run code on any OS platform it supports. Now, how this fits in is that the application, again, is at the top of the stack, but it's also at the least privileged and least trusted of your stack portion. The kernel itself, it's really a gatekeeper, and so it must be highly secured in layers of security. These privileges for applications and user space, most privilege for software running in the kernel. Ring 0 is your kernel, ring 3 is your applications. As you move up in utilization of your OS, you might have device drivers. And as you get closer to the kernel, the more privilege you have and more capabilities you have affecting input and output operations for applications and any layers below that. Device drivers can come in multiple flavors, and they're usually working in unison with your kernel to make use of your resources and take inputs and outputs from your applications, passing it through the kernel for further processing and routing. So again, the kernel is a highly specialized, efficient piece of code that takes input and output operations on behalf of your OS and routes and manages how your hardware interacts with your operating system. Examples of these kernels include Windows NT kernel, which stands for New Technology. And this ranges all the way from Windows NT 3.5.1, which is among the most popular, all the way through up to Windows Server 2019. It uses the same kernel family, but not the same kernel version. Linux also underwent a huge transformation. In the early mid 70s, there was a Linux kernel creation, and now we're on 5.7 as of the year 2021. Mac OS also uses its own kernel, which is called XNU kernel. And again, kernels are based on families that have different versions and they're usually compiled and targeted towards very specific operating systems for very specific use cases and functions. So what does hardware fit in if your kernel is always interacting with it? Well, we have examples, including your CPUs, hard drives, and random access memory, aka RAM, which is also noted as memory itself. Ultimately, you want high performance parts and hardware, the fastest you can afford possible. And really, all data inputs and outputs come from different peripherals. These peripherals also use a centralized event bus using signals on what's called a centralized board or a motherboard. These signals are based on ones and zeros on electrical currents and are sent from inputs and outputs, such as video cards being your output, inputs being your net card or output, and it goes all the way up to your CPU for processing, and any kind of data gets stored back into fast storage or slow storage, depending on what the need and use case is. This pipeline here is referred to as the PCI bus, Peripherals Component Interchange Express, and that's the standard we use today. So for those of you who have built gaming machines and other rigs, perhaps, you've used the standard in the past, and you will still use the standard sometime likely in the near future. Now, these signals of ones and zeros are represented as single binaries. Binary is the single base 2 need for your OS and really computing to operate on. Base 2 because you only have 1 and a 0, true or false. 1 equals true, 0 equals false. The simplest form and the smallest form you can actually talk to a computer with is called bits. Now, bits in the main aesthetic of all this is that base 2 operations of true and false include lots of different things. In fact, let's take a look at that real quick, and we'll clear our slide, and let's look at bits one more time. Oops, let's go back. Bits one more time. And we have bits here. We have a single 1 or 0. Now, when you think about that, if computers can only speak in 1 and 0, and we know they're base 2, true or false, right? This is actually called machine language. Machine language. And that 1 or 0, true or false, on or off, is really converted from the electrical signals on your motherboard and electronics into those logic gates that go into true or false conditions at the analog level. When it becomes the data digital level, that's when it gets converted from your CPU and other input and output devices into a digital format of 1 and 0 into data streams, rather than electronic gates of 1 and 0, opening and closing as true and false at the board or electronic level. So I wanted to give you that context before we move on. Now, because bits are the smallest way to represent data, 8 bits form a byte. So if you put ones and zeros together in a continuous row of 4 and 4, or 8 together, any combination of 1 and zeros, you have 8 bits, and that is 1 byte of data. Now, as we move forward beyond bytes, we have into the 1024 kind of notion, and we start grouping them in intervals of 1,000. Now, why is it truly 1024 over 1,000? Well, if you think about base 2, if you calculate the closest number to 1,000, it won't ever hit 1,000 if you go in increments, exponents of 2, right? 2 to the power of 2 and so forth. That goes to 1024 if you would calculate things in groupings of 1,000 at a time. Now, let's go back. We also have 1024, so 1,024 bytes is a kilobyte, and it keeps going down to megabytes, gigabytes, terabytes, all the way through exabytes. And there's many other acronyms there, but ultimately, when you're a user, you're probably dealing with mostly terabyte through kilobyte size ranges. And that's partially because of your hardware, practicality, cost, savings, etc. So really, these last two, petabytes and exabytes, are really about data centers. These data centers have a large amount of need, and we'll just go ahead and say DC here, because my handwriting is quite terrible. Data centers, DCs, these are what enterprises uses, and that's a lot of data. 1,024 terabytes. 1,024 terabytes is an exabyte. Wow. When you think about it relative to your consumer grade hardware, you might be using only 1 or 2 terabytes at your local home. That's 1,000 times more and 1,000 times against that when you're looking at data center constructs and storage needs. So really, you'll see those more in terms of enterprise storage requirements rather than you on the individual smaller scale. Now that storage of data of ones and zeros gets fed into input devices, whether that be other hardware or whatever you may want to call it. The CPU, or the central processing unit, is really there to process the ones and zeros and make calculations on them. If they have temporary variables or calculation intermediary steps and they need to keep reusing that calculation, they might put it in local cache. That local cache may be level 1, 2, 3, 4, all on the same chip. Actually on the chip, not actually external to anything, and that makes it for a very fast computational need and power. Ultimately, your ones and zeros finally get processed after calculations into something back out to whatever device it needs to go to, such as if you have an input of data coming in from your network card, your CPU processes the instructions based on your application or your program, right? Your app or your program. Program does something with those ones and zeros and outs it back again. So your output device might be your monitor or to send to your web browser if you're surfing on the web and representing google.com, for instance. Now, when we look at CPUs, some examples include Intel, AMD, and recently Apple M1's different chips. Now, they all have different architectures and architecture supports. It's up to you to determine which operating system, which application does support which operating system type and architecture types. So you really have to choose your hardware carefully based on the needs of what you're doing for. So remember, ones and zeros at the analog logic gate level for the electronics beneath. When you get to your data level at processing data bits at your CPU level, that's when it starts really turning into data and it gets restored back into your data storage, which is either memory or secondary storage like hard drives. Now, speaking of memory, memory is that scratch pad for your CPU to have extra buffers for. What does that mean? So your hardware of memory is really temporary storage space for something. Loading in applications, right? If you loaded an application into memory, you're running that application because it's the fastest way to run it. You don't want to run it from a hard drive. You want to load it into memory for best processing performance. You might also load variables. All right, so user inputs, stuff like that, are also commonly loaded into memory, or actually temporary calculations, right? Math, integers, anything else that the CPU might need might go into memory if it can't go into the local cache storage on the chip itself. Now, there's something also interesting about this is that you have something called DMA, direct memory access. So if your CPU is up here, direct memory access basically says I'm skipping and have a direct pipeline bus to the memory location itself, even if it's external to my chipset, because that's still faster than going through a centralized routing area for other signals to occur. So think of CPU and memory as going hand in hand, and CPUs don't have anywhere to store anything in a fast-paced manner without memory. Otherwise, we'd have to be on a very slow computing power if we had to rely on storage from our hard drives. Now, memory comes into multiple different forms. As you can see on the slide, there are direct chips that you can insert inside your system board. So these are commonly desktop chips and laptop chips, but you can also have soldered and non-replaceable chips from the manufacturer, or you can have direct CPU cache memory built in on top of your processor. But remember, that's a very small amount made for high-powered processing requirements and not meant for loading an entire operating system in. Now, data storage, we think about primary and secondary data storage. Hard disk, anything slower is considered secondary storages from a compute standpoint. So what happens is your operating system, in tandem with your CPU, says, I need to load program A into memory. I'll create a virtual mapping, my own map of allocable addresses for what should be scratch pads for the CPU. So CPU will try to load that into memory from your OS. And we're saying we have application A. If application A is loaded into memory and if we need application B to be also loaded, let's say I pause application A, I need to focus a new tab, and this happens very, very quickly, which hopefully you won't see a difference in. And what happens is we actually have what's called a swap. What happens is that application A now will be written to disk, which is slower, and it'll still run, but we don't make it a priority anymore. And if B took priority, we'll load that into the physical memory, the fastest memory, which is our primary memory, and that is swapped, aka a swap space. When we say swap space, we're swapping pages of data into your disk, and it's actually quite slow. So you only want to do swapping when absolutely necessary. And the more memory you have, right? In the past, people said more memory, the better. It's because you could load a bunch of applications into faster memory using chips rather than worrying about slower moving disks. Now, what makes for good memory storage? Well, we got to think about it. Hard drives make good memory storage locations for swapping and for long-term needs because you can write many times and read many times. Flash drives are becoming more reliable, where mean time between failure between lots of reads and writes are not going to kill them faster. But Blu-rays and DVDs, let's think about that. If you burn something to a optical media, is it usually only once, and is it usually really slow? And the answer to both of those is yes. Relative to these two options and above, you have no really good recourse for using Blu-rays and DVDs as swap space. Because why? Well, you can't write to them quickly, and you only write once in most cases. So using hard drives makes more sense because one, they have a longer lead time between failure than USB flash drives. They're made for that kind of input and output constantly, day in, day out, running constantly. But they're still slower than a dedicated memory chip for memory. So for your OS, we'll use a combination strategy with your kernel and figure out what is best to be on the operating system, loaded into memory or loaded onto disk, depending on what your load might be. So if your process priority was you using your browser would be likely loaded into your memory. And anything else behind the scenes that you're not really using and not really caring about will probably be swapped into disk. All right, so when we talk about inputs and outputs, putting in a cable, it doesn't matter what the physical medium is, you have inputs of ones and zeros coming in, and you have them going out. Every modern computer has network interface cards, NICs. These cards are really primarily for communication with the outside world or other computers on the network. So you have Bluetooth, wireless, Ethernet for wired, and they're really just there to make life a lot easier, right? You cannot install packages and update your operating system without networks. So these specialized devices are there for you to communicate in and out of your operating system accordingly. And of course, those bits going as input for your CPU and eventually return as outputs from your CPU if you're sending data back out. We have another concept called virtualization. Now, virtualization takes use of the idea that if you have one computer, typically in the old days you had, well, let's say that computer had to run OS Windows. And you had another, and you had app 1 that ran on that. But then what happens when you need to run an app that used app 2, and that needed Mac? Well, the only thing you could do at the olden days is really buy another hardware that would support the Mac and run that accordingly. But that's really a waste of compute power. So let's say you had a really powerful first computer here. If your first computer had 100 CPUs and your second computer had 10, and your application only ran with 2 CPU, you actually are wasting quite a bit of resources because a lot of that stuff is idling. And so why duplicate all that effort? Here's where virtualization comes in. So a type 1 hypervisor is a very special piece of software that replaces your OS on bare metal. When we say bare metal, we mean installing it directly onto the system itself. Type 1 hypervisors are really there for to say, hey, install me on your server or your desktop, and From there, you can create virtual, logically distinct machines on me using all the resources you have, and you can run your Windows, run your Mac, run any other Linux and OS and application combination together on the same hardware, consolidating and cost saving and sometimes higher performing, because now you don't have two computers over a slower network together trying to talk to each other. You have it all inside logical programming board, virtualized networking, which could potentially be faster than a physical link somewhere else outside of that. So you have performance potentially, and you have cost efficiency, and that's why virtualization was so popular and still is popular. In traditional virtualization, you also have type 2. So think of not replacing your OS, you still have an OS like Windows, but you're installing another layer on top of that. So you have a type 2 hypervisor, and you install that software on top of Windows like a operating system sandwich, and then you would have your guest VMs running accordingly. Guest being isolated logically VMs that the operating system and the hypervisor are both hosting together. Let's illustrate this a little bit more clearly in the next slide. So type 2 hypervisors, you got to understand, are a sandwich. Now, they have a performance impact. You still have a host-based OS. So if I have a Windows operating system, I install my hypervisor, which could be VirtualBox or VMware on top of it, I have an additional host OS taking out resources when I could give it back to these VMs right here. Hence the performance impact. However, there's an advantage to this. The advantage is, what if my hypervisor didn't have true hardware support for everything I had in my hardware, and I needed that the extra support? Well, my host operating system, as long as I have all the drivers for that, has all those drivers that knows how to talk to that hardware. And so the emulation happening inside the hypervisor, that abstraction for me, is already being done, and the hypervisor software doesn't need to know how to deal exactly with those drivers. It just relies on the OS itself. Now, that's a gross oversimplification, but that's just how it is in the most general sense. In addition, we're still getting our resource consumptions, and we can run any guest OS combination we desire and choose. Going back to type 1 hypervisors, think of one lesser number means one layer less. We are replacing the OS, and while we're replacing the OS, giving back resources to the hypervisor and bare metal and guest OSs, well, now we have an issue of the portability. What if we didn't support all the drivers? That hypervisor software replacing my OS now needs to know how exactly to talk to and has to have the right drivers for my exact hardware, and it may not always be the case. So if you don't have certified equipment on certain hardware configurations, you just build something and hope that it works, you will have less of a likelihood of working out 100% as from a type 1 versus a type 2 hypervisor. So performance on this side, and then portability and compatibility on this side. Now, yet another abstraction, and really kind of a second abstraction is, well, we have type 2 hypervisors right here. But you notice something here. We have to manage a host OS, a guest OS, and then we have to make sure that we have everything installed so that each application can run exactly how it needs to run. Libraries. So libraries are sections of code, functions, anything else that you externally reference that you did not use in your original code. Hence, a library of stuff, a library of knowledge that you're referencing to. If each of these applications are running a different OS and instance, and they can run the same libraries, you still have to create 3 different virtual machines for each one, and you have to manage 3 instances. So now you go from 1 host to 4 if you're using 3 different VMs with that host. Not really fun. So what developers started doing was containerization started becoming more popular with Docker and many other formats. In fact, containers have been around since the 80s, but they weren't really popular because we didn't have enough compute to make it viable. Now we do have enough compute power, engineering, and new technology to take advantage of this. And so now we have an OS that can handle all of that, regardless of your OS, as long as we have a container engine. When we develop a piece of software, all we have to focus on is the right reference libraries and our application itself. we contain it inside a container, hence container, and we say, as long as I have my libraries and other files in my packages, I don't care what OS you run on, as long as it has my container engine that I decide to use. I can also, the more you scale horizontally, you'll see that applications B and different variations and versions of application B can all use the same binary and libraries loaded into memory already, also saving that extra hence of copying multiple binaries and libraries across multiple operating systems. You can share the two if necessary or keep them isolated for security and compliance reasons. Up to you as a developer or as an engineer. Just know that containers provide that extra extraction of only having to worry about this. Right? I'm containing my application to what kind of functions do I need, what kind of source do I need, codes, other things that are dependent, as if I was installing an application from scratch, and I can move it to any operating system, any server that I want, as long as it runs the container engines platform. Now, one additional abstraction is serverless. Now, it doesn't mean that servers don't exist. It just means that you don't manage all that what you did behind. If we look back at hypervisors, we had to manage OSs. We look at containers. We had to manage still libraries, even though we didn't have to manage the operating system supposedly anymore from a function standpoint. Serverless takes it to one step further ahead. And we're saying, well, we don't manage any of that. We only manage the code we need to manage. Right here, right here, right here, and right here. So instead of worrying about one monolithic, huge source code source, we can say we can manage only just separate functions. And I don't even want to manage the libraries or how my application runs in that environment. You manage the environment, you manage the infrastructure, I focus on the code. That's essentially what serverless development means. And who's this you? Well, the you is cloud providers typically, which is Amazon Web Services, which they're Lambda functions. Lambda is a specialized function inside programming languages, and that just means temporary function. It's only run when it's called, and it goes away when it's done running. Microsoft Azure, with its cloud services, uses Azure functions, and if desired, or if you wanted to use a different third-party cloud solution provider, and they use Apache OpenWhisk, you can be open source. Or if you had a dedicated team for running all your serverless infrastructure, you can actually install this locally on premise, have a different team run that with a different responsibility, and you as a systems engineer, systems architect, or developer can focus purely on the code and the development situations that go with that. Now, serverless is also way more than that. So you must also think about cloud compute as platform as a service. Decoupling. So instead of creating one large application over a long period of time, why can't I reuse this? Surely there is really good code in many different functions, and so why should I have to rebuild it each and every time? So teams have started splitting into different ways of smaller groups of microservices, and they want to create code that's reusable in many different applications. So you could reuse code from this function or this function. And so we call that decoupling, event-based programming microservices architecture. From a user standpoint, they don't know the difference. And really, it's a great way to say, hey, if I want to upgrade and take this down and upgrade it to a new version, it doesn't affect other pieces of the application, so long as we have a failover or some other kind of enterprise backup solution for that. And serverless is really easy to do that because you can create a second Lambda function or create another function that takes its place temporarily while you do another application and just change the routing flows of it. Serverless compute is really future-based programming, decoupling everything. And while it makes it simpler to develop in terms of getting it off the ground, it makes it harder to trace, harder to track where things are going because you could have reuse everywhere. But it also makes for a highly resilient, highly scalable set of applications. Now we're coming up to our break. Let's go ahead and take a break, and then we'll get right back to our demonstration right up ahead. So take your break, and then we'll see you back for your demonstration with me. Hey, welcome back. I hope you had a great break. Let's take a look a little bit about where our resources are and how it operates, and really get to showcase what it looks like in Windows as well as Linux on what we just talked about. I want to open up Task Manager. And Task Manager is a resource management and monitoring tool From here, you can see your different applications running. I have multiple instances of Chrome, and I can end that task accordingly, so I can manage those applications running and services running. Remember that services are a very high load or high need for staying online. And right here in my processes, it's saying that we have an application that's taking up a good chunk of my memory and resource utilization, including my graphics power unit of very high power usage. Ultimately, we have performance as well, and we can see our memory consumption accordingly and go up and down as applications are making processes and doing stuff with it. And if I move this more and more, I'm still increasing my CPU utilization because it's still got to render and process what my mouse and cursor is doing. Now, let's take a look at our type 2 hypervisor and our guest VM. I have a single guest VM in a suspended state. We have 4 gigs of RAM and 2 processors allocated to it and many other peripherals. I'm going to resume this, and it's going to load this back into memory. Notice how my CPU and memory will start increasing over time as it gets loaded, and that is what is happening. Now that we have our guest VM running, we can actually see the same thing of what the VM is possibly running. So for that, I'll use the top command, and then it's just like Task Manager, only the fact that it's only in text terminal. We have our free memory and swap spaces, CPU utilization, and some of our processes that are running accordingly in real time. We can also press C for color and command and things like that, but I'm going to quit that. We're also going to use PSEF, which is a great way to showcase all of our processes running at any one point, and that's quite a bit of stuff. So I'll go ahead and use clear and do PSEF head, and we'll get the first 3 lines, and we're saying, hey, look at what we have. We have a user running something, we have a process ID, a parent ID if it has a sub-process routine, and then the actual command ran with the prompt. We'll just go up, and we'll say, show me the first 5 instead. Notice that this one has a parent ID of 2. So we're saying this process was created by nobody else. It was just created. But these processes are sub-processes from the original 2 and 3. So it's kind of like a chain of processes together. Also, I can use free to show me the different memories free and not free. I can use a -H for my parameters. And of course, just like this with Task Manager, I could do so accordingly with Linux. Now to see what kind of partitions and how much my in-use utilization is, we have a utility called df, and we can use -H accordingly. And then we can say that what's our utilization here. And this is the same as you go into the actual C or your My Computer and seeing where you are in the grand scheme of things and what my utilization is across multiple drives inside Windows. So I just wanted to show you case that a little bit more. And then also, what does our data storage looks like? And what is our units of measurement? So if you did an ls on, well, we have a downloads, we'll do desktop. Well, we actually go to desktop, network and directory. We are back at my desktop. And we're going to go ahead and ls. Now we'll do ls-lah to showcase the size of the different files, and this is in bytes, and then it turns to kilobytes if necessary. But if you didn't have the H, it'll show always in bytes. And it'll show us that 4K is 1024 multiples of the byte count here. So wanted to showcase that the metrics still go on, and the H, in most cases, if you're looking at DF, right, you have your byte count versus 1K blocks versus H for human readable, which groups them into the size margins that we're looking for earlier. Now, let's pause here and let's think about where our kernel space are and where our user space are. Are we in kernel space? The answer is no. We're actually in user space because we're running applications from the command line. We're not doing anything with the kernel. So let's go ahead and get right back to our presentation about the different business requirements and how we can get into that mix and really set that tone here. All right, So we have systems architecture, designs, and business requirements. And we need to really understand what the business needs and turn that back into designs and technical expertise of your system. First and foremost, we have a business requirement document, also known as a BRD. So let's go back into this and get our pen, and we have business requirement document BRD. And that basically says, what are my use cases for the application or the systems I'm building? Requirement 1 through 3 are in, and we're going to say, what's the priority? What's the rationale? Is it optional? Is it required? Is it required for phase 1, 2, and 3? Those are all hashed out in this document, and some of the stakeholders that you should keep in mind as you build out anything and change anything is legal department, compliance, the information security team, and ultimately the project management office to help you execute this. If you're a consultant like myself, you can also use the statement of work, but it's not the same as a business requirement document. A statement of work really says what my deliverables are, what my cost is usually, and the milestones to measure how far I am in this project. Now, this is not the same as a project plan, but it usually includes a high-level summary of a project plan. Deliverable 1 is due here, possibly here, and what are my steps to get there and resources that are required. A statement of work is also called a SAL in most cases. And basically, as a consultant or anyone doing work internally or externally to customer-facing items, you should know that a statement of work means just that. This prevents scope creep and other resource consumptions that are not part of the initial discussion and agreed upon terms. Also, you might have the responsibilities matrix. There's a swim lane called a RASCI chart, which stands for RASCI, which stands for responsibilities, accountability, supporting, consultant, and informed. And you might have different swim lanes, different functionalities, and different teams based on what is required to create this project, execute on it, and close the project out. And you'll have different operational duties along with whoever is on that team or the team name for each one. So for instance, we might have project planning, meet with customers, and we have the accountable party who's the owner of everything, the responsible party for executing on it, a party that will support those efforts, a party that needs to be consulted for maybe approvals, and a party that might be informed just as an FYI or copy on the email. Just as important is that we have governance, risk, and compliance. And with that, we have common activities inside our RASCI. GRC is what it's usually called. So you have GRC. And RASCI charts really help out with that. We say we have certain change requirements that we need to monitor before sending into production. Do we have security involved? Do we have everything we need from our architecture and design requirements? And do we have compliance and privacy's blessing from legal? All of these can be part of your RASCI chart as functional duties in everyday and project-based activities for your build-out. Now, as part of a great enterprise solution that whatever you'll build or whatever you'll tune and configure, and regardless if you administrate them or not, you need to have high availability. Examples include multiple devices, such as a primary and a secondary failover device. You might also have redundant failover networks. So in case one network goes down, you have a switch that bypasses and goes to another. Or you might have fail-open devices. Now, Palo Alto Firewalls is what is displayed here. It is actually a vendor of a very famous firewall vendor. But firewalls typically don't fail open, they fail closed. That's why you always put them in pairs. But however, a bypass switch can fail open, and if you have what's called copper links, basically wire connections that don't use fiber optics, it will create that physical connection and close that loop so that the connectivity between the next firewall and the switch can still happen, hence bypass switching. Those are considered fail open devices. But that's not always going to be the case, especially with security appliances and gear. Now, scalability is different from high availability. Scalability says, hey, I have 10 users today, and I need to have upwards of planning of 100 users tomorrow. How do I scale? Versus high availability, which says something fell over to the next thing, so we can still have continuous production somehow. So scaling up means if I have 2 instances here, 2 VMs behind a load balancer, 2 here, and 2 here, right? I have high availability because I'm in two different groups, and we have a primary and a secondary. So if one goes down, you can always send to the other. But here's the thing, though. I'm at capacity. I can't scale any further unless I add more VMs. And with a load balancer, especially in the cloud, you can do that. So if I need to add more processing power for anything that's inbound orders, I would add 2 more VMs on both sides, and now I have scaled horizontally. Scaling horizontally basically means that I'm adding more node and compute capacity as opposed to scaling vertically. Vertically means I'm saying, hey, this VM is too small, right? I need to have 4 CPU instead of 2. I need to create a bigger VM, hence scaling vertically as opposed to horizontally. So think of scaling horizontally as more total number counts on your instances and stuff like that, and total compute, and adding it that way, or vertically. If you scale out vertically, you're creating a bigger version of something, and you're not actually adding more nodes or any other computing instances. You're actually just scaling up, basically adding upgrades to an existing system and not retiring them out. Well, that's it for today's lecture. I hope you had a great time, and I'll see you in the next lecture, hopefully soon.